Today, we are going to master one of the most essential operations in computer science, inserting a new element at the very beginning of a singly linked list. By the end of this session, you will be able to map the anatomy of a node, confidently connect a new node to the front of a chain, and write out the formal algorithm from memory. This diagram shows the structure of a single node, split into two distinct components. The first part is the data field, holding the actual value to store. The second part is the next field, holding the exact memory address of the following node. Now, let's look at this diagram showing a standard existing list with 3 nodes. Notice the box on the far left labeled Start. The start pointer currently holds the memory address 1000, which points us directly to the first node in our chain. It is vital to understand that Start is not a node itself. It has no data field. It is simply a directional container holding a memory address. This separation of the pointer from the data is what allows us to redirect the flow of the entire chain by updating a single value. When we talk about insertion at the beginning, our goal is specific. We need to introduce a brand new node containing specific data and successfully wire it into the sequence before the current first node. First, the system allocates memory for a new node at address 5000, storing the value 10 inside. Next, we copy the start pointer's address, 1000, into the new node's next field, linking them. Finally, we update start to 5000, making our new node the head. With the memory addresses handled, we are left with this clean logical sequence. Start points to 10, which flows to 15, then 20, then 25, and finally terminates at null. There is a strict order of operations here. If you reverse steps 3 and 4, updating the start pointer before you connect the new node, you will overwrite the only record of where the rest of your list lives. The original nodes will be permanently orphaned in memory. To lock these mechanics in, we will now test these steps by building a brand new list completely from scratch, beginning from a state where the initial start pointer simply equals null. Tracking our first insertion, we create a node with data 10. Since the list is empty, start is null. We safely point the new node's next field to this null value. Finally, the start pointer updates to address 1000. Our list now successfully contains a single item. Moving down the table, we initiate the second iteration. We create a new node for the value 20. We connect its next field to the current start address, linking it to the node holding 10, and then we update start to point at the new 20 node. Let's test your active recall. If we repeat this process one more time to insert the value 30, pause the video and predict exactly what address the new node's next will point to and what the start pointer will become. Let's verify your logic on the final rows of the table. The new node for 30 sets its next field to the old start address, which is 2000. Then start updates to 3000, confirming the node holding 30 is now at the front. Notice the practical consequence of this specific algorithm. Because we are continually forcing new data to the front, inputting the sequence 10, then 20, then 30 naturally constructs our list in reverse chronological order, 30, then 20, then 10. Having executed the process manually, we can now easily read and understand the formal algorithm for inserting an item at the beginning. Step 1. Create a new node called New. Step 2. Store your item in the new node's data field. Step 3. Set the new node's next pointer to equal start. Step 4. Set start to equal the new node. And step 5. Stop. Now consider the performance characteristics of this algorithm. During every insertion we just practiced, we never had to travel, or traverse, down the existing links to find the end of the chain. Because we are only ever interacting with the start pointer and the very first node, the overall size of the list does not matter. Inserting a node at the front of a small list requires the exact same number of operations as inserting one at the front of a massive list containing millions of nodes. Because the execution time is completely independent of the list size, we can confidently state that this algorithm operates at 0.1 constant time. It is an incredibly fast, highly efficient operation.